Hello everyone, my name is Xujun Han from Carleton University. Today I will present our paper, Overcoming Catastrophic Forgetting for Continual Learning via Feature Propagation. So what is continual learning? The model learns a sequence of tasks one by one and is expected to perform well on all learned tasks. The model can only access and be trained on one task at a time. And so the point is the model has to overcome forgetting on previous learned tasks. For the offline continual learning, the model can be trained on the dataset for multiple times. For the online continual learning, the model can only see data once. So for this paper, we focus on the online continual learning scenario. There is a kind of continual learning methods called rehearsal-based methods, where a small memory set of past data is reserved and can be revisited multiple times during learning the new tasks. Consider a stream of unknown distributions d1 to d capital T. For rehearsal-based methods, at time t, there are two datasets on hand, dt for the current dataset and m for the memory set. So the objective is to minimize loss on both datasets, which is also known as experience replay. Our method contains three parts: experience replay with feature propagation, contrastive representation rehearsal, and supervised contrastive replay. Suppose the model has two parts, a feature extractor per se and a classifier F. We denote per se O with the model state before learning task T, after learning task 1 to T minus 1, and then we apply feature propagation procedure to the training datasets dt and m in the feature space. The example embeddings derived from per-se are amended by fusing a weighted sum of all data embeddings by per-se O. So we got per-se tilde of x equals y minus w times the current embedding of x plus a w times a weighted sum of the previous embeddings of all data points. The propagation rate aij for data xi and xj is computed by their Euclidean distance. So by this way, we hope the current feature space can absorb some information from the previous feature space. The fusion of the two terms is motivated by the exponential moving average, which can move forward without forgetting the past. The mandated experience loss is defined by the loss function on the new feature space by feature propagation. Next, we use a contrastive loss to enforce the example embeddings to stay near the previous corresponding ones to protect the representation space from dramatically changing after being trained on new tasks. The proposed contrastive loss is defined to push the current embedding of x to be close to its previous embeddings and away from the previous embeddings of other data points. Up to this point, we got the contrastive continual learning with feature propagation method by combining the amended experience replay and the contrastive loss. To further improve the feature space, we apply a supervised contrastive loss to push in the embeddings of the same class to be close and the embeddings of the different class to be far apart. By this way, we try to eliminate the domain and class shifts between different tasks. Now we got our final objective by combining the amended experience replay, the contrastive loss, and the supervised contrastive loss. In the experiments, we compare our methods with several state-of-the-art continual learning methods on 6 datasets. We use average accuracy to evaluate the overall performance of models on test data of all same tasks, which indicates the average accuracy on test data of task 1 to T after the model has learned continually up till task T. This is the main results of our paper. The first line joint serves as the upper bound. and fine-tune its lower bound. The last two lines is the results of our methods, and we can see our methods can achieve the best on almost all cases. This figure gives the evolution curves of average accuracy on test data of all tasks as new tasks are learned. The red line with square marks is the results of our method, and we can see at most times our method is better than other methods. That's all for our paper. Thank you for your attention.